Today we're going to be talking about length contraction. So just as time dilation affects the amount of time intervals between reference frames, relative motion also affects the measurement of length. This is length contraction. So we have a thing called proper length. Now proper length is denoted by the symbol here. And it is the length of an object measured by an observer who is stationary relative to that object. It is the length measured in the object's own rest frame. So proper length, just like with proper time, it is measured by an observer who is stationary relative to that object. So for example, sorry, not proper time, this is proper length. So for example, an astronaut on a spacecraft measures the length of their spacecraft using a ruler they are carrying. Since both the astronaut and the spacecraft are stationary relative to each other, the astronaut measures the proper length. Proper length is always the longest length that can be measured for an object. Now, there's also relativistic length, denoted by L. It is the length of an object measured by an observer who is in motion relative to that object. So, an observer on Earth measuring the length of the same spacecraft as it passes would measure a shorter length than the astronaut on board. The spacecraft appears contracted in the direction of motion. The relativistic length is always less than or equal to the proper length, and the contraction only occurs in the direction of motion. Dimensions perpendicular to the motion are unaffected. So, relativistic length is always less than or equal to the proper length, and contraction only occurs in the direction of motion. Okay, so there's a few other key points that we'll talk about. Length contraction is not a physical compression of the object. The spacecraft is not actually being squeezed. It is a genuine geometric consequence of how space behaves at relativistic speeds. Different observers in different reference frames simply measure different lengths for the same object. So just like with time dilation, the effect is negligible at everyday speeds, and it only becomes significant as velocity approaches the speed of light. At the speed of light, the contracted length would approach zero, though no object with mass can reach the speed of light. So to summarize, proper length is the length of an object measured by an observer, stationary relative to it. It is always the largest measurable length. Relativistic length, L, is measured by a moving observer and is always shorter than proper length. Contraction occurs only in the direction of motion and is a consequence of the constant speed of light, not a physical compression of the object. How to calculate the relationship between L and proper length will be covered in a future video. Follow for daily QCAA content.